Hey guys, my name is Trevor Sullivan. I am a solutions architect with StratusGrid, and in this video, I wanted to talk a little bit more about Amazon DynamoDB. In the last several videos on our video channel, we've been talking about using the Rust SDK for AWS in order to access the DynamoDB APIs to do things like creating a table, setting up our table schema upon creation, inserting items into the table, doing queries over the table, as well as table scans, which are more expensive operations but allow you to retrieve every single row or every single item of data inside of your DynamoDB table. So the topic that I wanted to focus on in this particular video is actually a concept known as local secondary indexes. There's actually two different types of secondary indexes that you can create in Amazon DynamoDB. The first is going to be local secondary indexes, which have some limitations that you'll want to be aware of. And the second type is called global secondary indexes. So we have LSIs and GSIs, depending on the pattern of queries that you're planning on writing against your data in your DynamoDB tables. So we're going to be talking about what a local secondary index is. The documentation for DynamoDB does a really great job of breaking down the reasoning why you would want to use one type of index versus a different type of index. So we'll be exploring that. We'll also be taking a look at the AWS Management Console here to learn about how to create a table interactively through the AWS Management Console with a local secondary index, just so we can understand things a bit more conceptually. And then we'll actually talk about how to create these local secondary indexes using the Rust SDK for AWS. So let's go ahead and get started. So I've got a table right here in the AWS Management Console called Trevor Products 2. And if you've been following along with any of my earlier videos on DynamoDB, you'll probably be familiar with the simple table schema that we have right here. So if we take a look at the items, you can see I've got a category. I've just got a few items in here with a category of kitchen. So I only have a single partition key value in here. I also have a product name. I just prefixed that with P underscore because the terms, things like category or name, could potentially be reserved keywords in the DynamoDB service. So I just wanted to make sure that I had a unique attribute name for each of the attributes in my table. And then I've also got the is available here, which I'm just going to set as a string value of either yes or no. And this is going to be our secondary indexes sort key or range key, depending on your preference of terminology. We have the partition and sort key, and then we have hash and range key. Those are two different terminologies that we can use to refer to the same thing. So anytime that you see hash key, it's going to be the partition key, which is going to allow you to partition your data on the actual backend DynamoDB storage by specifying different values for your partition key. And then the range or sort key is going to be the value that the table storage actually sorts your data on, so that when you are querying your data later on, when you're retrieving data from the table, it is able to do more efficient operations against the table storage and return your queries faster and at a lower cost when it comes to read capacity units for your table. So this is my actual table schema right here. I've got my primary and or I should say my primary key, which is actually a composite key of my partition and sort key fields here. And then if I actually take a look at the table configuration here, so let's go back to our table configuration and then go to the indexes tab right here. Normally, when you create a table, you won't have an index unless you explicitly want to create one. But right here, you'll see I have a global secondary index option, and I don't have any global secondary indexes. I could go ahead and create one on this existing table. But then down here at the bottom, you're going to see that I have a local secondary index. And so what the local secondary index allows me to do is to specify a different range or sort key so that I can sort my data based on a different attribute than the sort key that's in the table itself. So you can kind of think of it like almost having a duplication of your table data, but it's going to sort the data differently on disk than the table configuration itself has. So in this particular case, if you take a look at my local secondary index configuration, you'll see that the partition key is the same as the table, right? The category field is going to be our partition key, And for local secondary indexes, you actually have to use the same partition key as the underlying table that the index references. That same constraint is not necessary for global secondary indexes, but that's beyond the scope of what we're talking about here. We're just going to focus on local secondary indexes for now. So the partition key has to be the same, but what you'll notice is that the sort key is actually different. So I can sort on the isAvailable attribute within a given partition value, whereas if I take a look at the table configuration, my sort key is actually the name, so that I can have unique product names, because the sort key value for each item needs to be unique, as does the partition key. So combined, the partition key and the sort key have to have unique values, but then I can add on whatever other attributes I want to. So I can't have duplicate product names within a partition. I could have the same product name across two different partitions if I wanted to, but if I tried to create two of the same product names under the same partition key, then it's ultimately going to overwrite the original item that was in the table. It simply doesn't allow you to create multiple items with the same partition and sort key. However, local secondary indexes actually allow you to kind of work around that. So when you have an index, your sort key can actually have duplicate values, because the underlying table itself has unique values for its partition and sort key. But since we're basically creating a view of the data in the underlying table with the index here, we can actually have duplicate values here. So isAvailable could say yes, 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 yes for different items, and then no, 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 no for other items. And that is basically how an index works. We don't have that same constraint because the local secondary index isn't a unique table. It's simply a view or a perspective of the table that is actually backing that index. Now, something else that you'll see in the index configuration for LSIs here is the projected attributes field. And we've actually talked about attribute projection when we have explored queries before, because you don't have to select every single attribute from every single item. An item could have 10 different attributes, but if I only need 3 of those, I can actually project specific attributes as part of a query. And when you create a local secondary index, you actually have the ability to specify certain attributes that you want to project into the LSI and actually skip including certain attributes. However, something that's really interesting to note is that, let's say, for example, that back in our table here, let's take a look at our table items really quickly. Let's say that we only wanted to project the category and isAvailable, and we didn't want to project the p_name attribute into our local secondary index. So basically, we're just projecting 2 different attributes, and we're skipping over one attribute that exists in the underlying table. Well, if we decide at some point that when we query that data from the index, not from the table itself, but from the table's secondary index, we can actually specify attributes that are not included in the projected attributes on the LSI. So even if we create the LSI to only project p category and isAvailable, we can actually still request p_name. However, there is a caveat there, which is that there is an additional fetch operation that has to occur in the DynamoDB backend, which will ultimately impact the performance of your table during those queries. So the takeaway here is that if you ever plan on querying an attribute through your index perspective of the underlying table, you'll generally want to make sure that you are projecting all of the attributes that you're going to be retrieving during a query operation from the index. Otherwise, you will have that performance hit. If you're only occasionally going to be querying a attribute that's not projected into the index, then you're probably okay with not including that particular attribute into your local secondary index configuration. Now, I say all of this because the local secondary indexes are a lot less flexible than global secondary indexes. So if we go back to the table details here, and go over to indexes, you'll see that I have the option to create an index, right? And you're like, oh, well, I'm going to go ahead and create an LSI, right? Well, when we hit that button, it's going to take us to create a global secondary index, not create a local secondary index. You'll probably think, all right, I'll just hit the cancel button and find the button to create a local secondary index, right? Well, not so fast. You can't actually create or delete, for that matter, a local secondary index once you have created your DynamoDB table. So what this means is that if you're going to declare one or more local secondary indexes on your DynamoDB table, it must be declared at the creation time of the DynamoDB table. I cannot go into my DynamoDB table configuration and create a local secondary index or delete one after I have created the table. So you'll want to be very thoughtful up front about the different methods that you're going to be querying data from your DynamoDB table to ensure that you have the necessary local secondary indexes configured on your table before you actually create the table itself. Now, one thing you could do is create backups of a table, and then you could create a new secondary table that has a new configuration with new local secondary indexes, and you could actually migrate your data from the old table into the new table, but that does require some application downtime as you're cutting over your application from the old DynamoDB table to the new DynamoDB table. Now, one other thing that I wanted to mention that is a limitation of local secondary indexes, and I'm going to point you over to some documentation here. So under the DynamoDB developer guide here, you can go down to working with DynamoDB and then click on this parent page for working with indexes right here. And this is a really comprehensive page that describes in depth all of the different characteristics or behaviors of global versus local secondary indexes. So local secondary indexes actually have a size limitation. This is one of the things you'll want to be thinking about when you are determining whether or not you want to use the local secondary index feature. If you are ever planning on having a specific partition, like in my particular case here, I have a partition key of category, and I have things like kitchen or living room or bathroom or bedroom, different products that I want to list in my store. Then I need to make sure that each of those partitions, whether it's the kitchen partition or the bathroom partition or the living room partition, none of those partitions can exceed 10 gigabytes in size here. If you try to insert an item into a partition and that would cause the partition to exceed 10 gigabytes in size, you'll actually get an error back from the service saying that the partition size has been exceeded, and it will not allow you to insert new records into that particular partition. So just be aware of that limitation as well. All right, so we've talked a little bit about the limitations here. I would encourage you to read through this documentation so that you understand all the limitations. One other thing that I did want to mention here is that as far as table consumption goes, remember that you have two different billing modes for the DynamoDB service. When you create a table, you have on demand, which is also known as pay per request. You also have the provisioned throughput capability where you can specify read and write capacity units as a pre-provisioned capacity so that you don't have to pay per request. It really just kind of depends on how much traffic you're depending on throwing at the DynamoDB service to figure out which of those billing modes is appropriate. But that's really beyond the scope of this video as well. When you create a local secondary index, however, the read capacity units at query time are going to be used from the base table's configuration. You do not have a separate billing mode for your local secondary index and the underlying table storage. It's actually going to share that table's capacity, right? So you want to be thinking about this when you are specifying how many read and write capacity units you have for your underlying table in order to make sure that your application isn't going to run into throughput exceeded errors when you're running queries against the LSI as well as the table itself. On the other hand, global secondary indexes don't have that same limitation. They actually are going to have their own separate provisioned throughput settings for read and write activity. So just remember, if you're using LSIs, they have some limitations. One of those limitations is shared throughput for the underlying Amazon DynamoDB table. So those are most of the limitations that I wanted to cover here. So what we're going to do now is actually go ahead and create a table through the AWS Management Console here. So head over to the DynamoDB service. I'm going to be using the Northern California region here, but you can use any of the supported regions for DynamoDB here. And so I'm going to go over to tables where I have this existing Trevor Products 2 table right here that I just showed you. I have 3 items inside of that table, but we're going to go ahead and create a brand new one. So for the table name here, I'm going to call this Trevor-Products. I'm going to specify my partition key. I'll use P category as my partition key. For our sort key here, we'll use P name so that we can have a category for the product and a unique product name. And those are both going to be string values, right? So a string like kitchen for category, and then a string like pan or spatula or spoon for the P name, product name here. So for the table settings down here, you're going to see that by default, we do not have any local secondary indexes, and that is not editable after creation. I can create my GSIs if I want to after the table creation, but again, this is just reminding us that LSIs must be created at the table creation time. So I'm going to choose the customize settings option here. I'm going to choose DynamoDB standard. They also have an infrequent access or IA option for tables that are not going to be accessed as frequently. And then down here, I'm just going to specify the on-demand pricing mode. And now under the secondary indexes option, I can actually say, I want to create a local index. Now, this is where you want to keep in mind the constraints of LSIs. One of the constraints that we talked about a few minutes ago is that the partition key for the LSI must match the underlying table's partition key. So if I try to partition based off of something that is not valid, which it actually doesn't even give me a field here for, this is for the sort key, then it's not going to work, right? We have to make sure that we have the same partition key, and the user interface thankfully doesn't allow me to specify anything different for the partition key. For the sort key, however, remember that the underlying table is going to have p_name as the sort key so that we can have unique values for each of the products in our DynamoDB table. But for the sort key here, I'll just create a field called isAvailable, and that'll be the secondary sort key that we have in our LSI instead of the name field, right? Or attribute, I should say. So I'm going to create an index here called Trevor Products-isAvailable index. And then we also have the option to set our projections here. Again, you have the option by default to say, I want to project all attributes from every single item in my DynamoDB table into the index. However, you do have the ability to specify certain attributes that you want to include. So we could say, I want P category. I want to make sure I have P name, and I also want to have is available. So now I'm just specifying all of them individually by name. I could also say I want to go ahead and remove p_name there, and I only want the category and is available here. And then if I did want to query and include the p_name, I can still technically do that, but it is going to impact the performance of my table. And you can actually read a lot more about that under the querying and scanning an index document. And this is available over under the DynamoDB developer guide. What is DynamoDB? Go down to from SQL to NoSQL, managing indexes, and then querying and scanning an index. And this is going to describe some of the challenges that you have here. Actually, I think I was looking for a different document here. I think it's the same one under this section right here, but rather than looking at the parent working with indexes, you actually want to go down to the parent local secondary indexes. And then this actually talks about the implications of doing an additional fetch operation. So if we just search for fetch here, it talks about extra reads known as fetches under attribute projections. It does tell you that you can retrieve attributes that are not projected into an LSI, but that it is going to have a performance impact on your table. All right, so what we're going to do is head back over to our console here. I am going to go ahead and include p name here as well, and then we'll just hit the create index button. Then we'll just go ahead and scroll down. We don't need to change any other options and say create table. Now, once our new table is created here, it'll take just a moment to actually create the table as well as the underlying index. We can drill into that table. Once it's active, drill into that table, we can see indexes right here, and now we have local secondary index with our partition key and our sort key. So remember, the partition key for LSI is always the same as the underlying table, which is P category in this particular case. So now what we can do is explore our table items and then click on this button here to create a new item. And you'll notice that the attribute for the LSI is actually optional here. It doesn't include that because we're only considering the composite primary key, which is made up of the partition and the sort key for the underlying table. So for P category, we'll say kitchen and then say pan, 9-inch, and then we're going to add a new attribute here called string type. And this is going to be the is available, and we'll just set it to yes. All right, so now we've created one item in there. We could create another item. We could specify a different option here. So let's do queen bed sheet, and we'll add in the is available. We'll go ahead and say yes and create. And then we'll do one more item here. Let's do bedroom and then lamp, and we'll add the string is available, and we'll set it to no. All right, so now we've got a few items in here. We have two different partitions. We have a bedroom partition and we have a kitchen partition, and each of those has a product, and it has the is available attribute here. So now what we can do is actually query the data from either the table's perspective or from the index's perspective. So when you go into the scan operation here, so we're under our Trevor products table right here, and then you do a scan or a query operation, right? And if you remember from my video on queries, you actually have to specify which partition you want to query from. With table scans, they're lower performance. They take a lot more read capacity units from your table, especially large tables that need to scale. And so with a scan operation here, we can just scan over the table, or we can actually select one of the local secondary indexes that we want to scan across. So you'll notice that in this particular case, it used 4.5 read capacity units. If I read from the underlying table itself, it only uses 2 read capacity units. So even with just a few items inside of my table, you actually see that querying that data using a scan operation through the secondary index is actually having a pretty big performance impact on this table. However, we can also do a query operation here, right? So if we query the table directly, I could say, show me bathroom products, right? And I don't have to specify a sort key. I only have to specify the partition that I want. And you'll see I get nothing back because we don't have any bathroom products. If I go to bedroom here, run it, you can see I get my bedroom products back. And again, we're still looking at the table, not the LSI. Let's do kitchen here. Run that query, and you can see I get that one item back. But now I can do the same thing against an index. I can query the index, but I have to specify which partition I am querying that index on. So we're going to plug in bedroom here. You'll see that actually consumed 1.5 read capacity units, which is significantly more than running a query directly against the table. So it's even more important that we are optimizing our queries by using queries instead of scans. And you also probably want to use sort keys here. And then let's try kitchen here as well, which should have a single item. And you'll see we actually used 1 instead of 0.5 or 50% of a read capacity unit. So these are some things that you'll want to be examining as you're running queries against your table versus a local secondary index. You want to see how that's impacting the number of capacity units that are being used for reading data. Now, write capacity units don't matter quite as much with LSIs. You still have to consider the fact that both the underlying table has to be updated anytime that you write or put a new item into the table, and the LSIs all have to be updated as well. So there is somewhat of a performance implication there, but the difference is that you don't actually write data into an index. The index is updated from the underlying table storage. So when you're calling put item operations, or if you're choosing this option down here to create an item, the reason that we don't get prompted for an index here to use P category as the partition key and is available as the sort key is because we have to specify the data to write it into the table, not writing data into an index. We simply don't write data into an LSI. So just be aware of that. All right, so now what we're going to do is actually talk about how to create one of these tables using the AWS SDK for Rust. So what we're going to do for starters is spin up a brand new project, and you'll want to have VS Code with the Rust Analyzer extension installed. I've actually got a video that introduces the AWS SDKs for Rust, so make sure you check out that video if you're unfamiliar with the process of setting up your development environment, and then come back to this video, and this should teach you how to actually use the DynamoDB SDK for Rust in order to create the table with the LSI. So in my terminal here, I'm just going to go to my project directory, which is Git here, and I'm going to do a cargo new, and we're going to call it sg-rust-dynamodb-lsi. And then we'll go ahead and run VS Code against that particular directory here, and that'll just scaffold out a brand new Rust project. If you've done any Rust projects before with Cargo, you should see that we just have our src folder with our main.rs file here. We've got our cargo.toml file. By default, there's no dependencies or anything like that. So we need to go ahead and do all the setup work for this project to bring in the AWS SDK, the SDK for DynamoDB specifically, which is a separate crate. And then we also need to set our main function up here for async. So if we turn our main function into async, we also have to specify an executor. So typically we just do cargo add Tokyo features equals full, and then we'll just add the Tokyo main attribute there, and that'll allow our main entry point to our application to be async instead of sync. Let's do a cargo run, and that should work perfectly fine here. Then we'll go ahead and add in the crates for AWS. So let's head over to the crates.io website right here, and we're going to search for AWS-config. This is the crate that allows us to set up our SDK configuration, like credentials through environment variables or your AWS credentials file. There's several different ways that you can specify credentials in AWS, and they're documented pretty well, especially in the AWS CLI documentation. And then we're just going to call this load from env function here in order to actually load the environment variables. So let's come back over here, and we'll go ahead and say cargo add. We'll do AWS-config, and then we're going to specify this feature here for this crate called behavior version latest. You don't really need to concern yourself too much with that. Basically, it just allows the developers of the AWS SDK for Rust to version control different breaking changes in their API, but generally you can just use behavior version latest. So don't really worry too much about the details on that. All right, the other thing we want to do is say cargo add the DynamoDB crate. So if we search for DynamoDB on crates.io, there is the AWS-SDK-DynamoDB. All of the service-specific crates, whether it's S3 or EC2 or any other service in AWS, have the AWS-SDK- prefix, and then whatever the service name itself is. So what we'll do is say cargo add AWS SDK DynamoDB, and we'll specify behavior version latest for that as well. And so now we're good to go ahead and start writing some code here. So for starters, let's go ahead and do AWS config, and we'll say load from env, and then we'll need to await that and assign the result to a variable like SDK config. And I'm not getting IntelliSense here, so I'm going to do an F1 in VS Code and say Rust Analyzer restart server. You can also just search for restart, and that should bring up that option there. And then at the bottom here, you'll see that Rust Analyzer is doing some work in order to set up all the IntelliSense stuff behind the scenes. So give that a moment to finish, and then you should be good to go with your IntelliSense. And all the error checking, all the linting and everything that it does behind the scenes is really nice. All right, so once we get our SDK config here, we're going to actually do some environment variables in our shell so that it just automatically discovers our region and our access key ID and secret access key. So what we're going to do now is create a DynamoDB client. So let's say let DDB client equal, and then we're going to drill into the DynamoDB crate. Typically, I like to do use AWS SDK DynamoDB as DDB for short, so that I can just use the DDB prefix here, and then say client, and then new. And then my IntelliSense looks like it's still finishing here. I don't know what's delaying it, but what we're going to do is borrow the SDK config variable here and pass that in so that we can construct this client object here. Looks like the IntelliSense is very slowly starting to work here. And then what we need to do next is to go ahead and call the create table operation. So we'll do DDB client dot create table. And I have another video that actually talks about creating tables, but this one is specific to local secondary indexes, right? So there's going to be a lot more code to creating a table using the Rust SDK than there is if you're just creating a table standalone without an LSI, right? So we'll say create table, and then we'll assign the result here. So we'll say create result equals the result of this table here. So what we need to do is basically configure all the input arguments to the table. And it actually really helps to have the documentation for the actual operation. So if we go back to the parent DynamoDB documentation here, and let's see, where is that? Right here. And then go down to the API reference. This is the actual REST API reference that's being wrapped by the Rust SDK for AWS. And then take a look at the create table operation right here under actions. And then what we can do is actually examine all of the input arguments. So it's actually fairly complex if you're using some of the more advanced features like local secondary indexes. It's actually very simple if you're not using any advanced features. From my other video, you probably saw that we just specify things like the table name, and we also specify the billing mode, which is right up here. And that's pretty much all you need to specify aside from the actual attribute definitions and the key schema down here, which specifies which attribute is going to be your partition key, which attribute is going to be your sort key, and what data types they are. Are they strings? Are they binaries? Are they numeric values? It's up to you what you want to do there. But when we do local secondary indexes, we have to give the index a name. We have to give it its own key schema here, and we can optionally specify a projection if we want to limit the attributes that we want to project into that local secondary index. By default, it's just going to project all attributes into that index, but if you want to limit it, you can actually change the projection type to include certain specific attributes by name as well. All right, so we're going to start with the simple stuff here. So we'll say .table name. I'll call this rust-ddb-products-lsi. And then we also want to specify our attribute definitions here. So we're going to have two different attributes that we add here. We're going to have our partition key and our sort key. So let's go ahead and set those up. If you take a look at the documentation for attribute definitions here, it's actually expecting an input of type attribute definition. So we have to construct this attribute definition data structure before we can actually pass it in as an argument to the attribute definitions method here. So I'll create one called part adder and create attribute definition. And then we'll do attribute definition. I think it's default, or is it new? Actually, I think we can just use the builder here. So we'll do a builder, and then we'll set the attribute name to p category. So this will be our product category. That'll be our partition key. And then we want to set the attribute type to one of the supported data types, which is the scalar attribute type. We'll do scalar attribute type, and you can see it auto-completes here. And then we are going to select the S type, which is the string type. You can also use the B for binary, N for number, and S for string type. Those are the three supported value types, I should say, that you can use for your partition key and sort key. So let's duplicate that down, and we'll create our sort adder, and we'll use p underscore name for that. And that's also going to be a string type. All right, so down here under attribute definitions, we'll pass in part adder, and then we'll duplicate that down, get rid of that semicolon because we don't want to terminate it. And then we're going to pass in the sort adder, and you'll see it says mismatched types expected attribute definition. That's because up here we have attribute definition builders. We actually want to call the build function on each of these in order to get the actual attribute definition. And then that's wrapped in a result type here. So because it's wrapped in the result type, we need to unwrap the final result as well. And that should give us the attribute definition data structure. The result type is just a standard Rust type that wraps either a successful result, which in this case is an attribute definition, or if something errors during the building process, it can return an error in addition. So in this case, we just call unwrap if we know for sure that it's going to be successful, which technically we don't know for sure, but this is a relatively simple operation here. So we're just going to call unwrap inline. So now that we get the attribute definitions in each of those variables, we can just reference them right down here. We also need to specify our key schema. So let's do let part schema for our partition key. Down here, we're going to call, let me put a semicolon here to terminate that line, just to make sure my IntelliSense works properly. So for the key schema, we need to pass in a key schema element struct here. So key schema. Our input is going to be one of those data structures, the key schema element. So let's go ahead and do a key schema element builder. We'll specify our attribute name. So in this case, P category is going to be the key type of key type hash or partition. Let me put this on a couple of new lines here to make things a little bit more readable. So we're specifying that the P category is going to be our partition or hash key. And then we can duplicate this down and say let sort schema be the key type of range key or sort key. It's the same thing. And we also want to call dot build on this, and that's also going to return a result type. So we want to return the unwrapped result there. And then we'll go ahead and just do the exact same thing for our range key. So now we have these key schema element data structures, and we can pass those into key schema. So part schema, and then we'll duplicate that line down and pass in the sort schema. Now, one other thing we need to do is set the billing mode. So right after the table name, I'm just going to go in and say set the billing mode to the billing mode enumeration here. So we'll say billing mode pay per request, and that'll set it to pay per request or on demand instead of pre-provisioned throughput. All right, so that should, in theory, work. Let's go ahead and actually test this out. So what we're going to do now is say .send.await. So we actually have to send the operation and await it synchronously in order to kick off the Rust feature that actually does the API operation. And then we'll just do a cargo run here and see if it actually works. So this will take a moment to compile. And then to validate that it works correctly, I'm just going to head back over to the AWS Management Console. And of course, I forgot to specify my credentials. So I've actually pre-generated some credentials. My other videos talk about how to generate credentials, but I'm just going to copy some credentials that I have already specified into my shell. So this will fail at first after it's done compiling. And so what I'm going to do is say in PowerShell env AWS access key ID equals this access key ID here. And this IAM user already has access to the DynamoDB service with the policies that I have assigned to it. Then I want to do set the secret access key equal to my secret access key value. And then we'll do env AWS region equals US West -1 for Northern California, which is the region that I was operating in the console before. Now we can go ahead and rerun this application, and it should pick up on those environment variables when we load the configuration right here on line number 6. So let's head back over here, refresh, and it looks like it is not creating it here. So let's go ahead and add some debugging. So what we're going to do is take this create result, and if it's an error condition, we'll say if create result dot is error, then we'll go ahead and print line, put in a placeholder here, and print out the create result dot error condition here. I probably just forgot something pretty simple here. And then after this, we'll go ahead and add in the details for the actual LSI configuration as well. So it's saying both the hash key and the range element have the same name. So when I duplicated my code here, I totally forgot that I had a p category as the hash and the sort key. So I actually want to change my sort key here to be p name instead. Let's do cargo run here. And this time we got no error printed out. So it looks like it was successful. Sure enough, here it is. All right, so the table that we just created here has no indexes, right? I've already covered this in my original video that talked about creating a table and inserting items into a table with the Rust SDK, but now what we're going to do is expand on this and actually add in the LSI configuration into our create table API call here, because the create table API call is a single API call, but it actually includes the LSI configuration as part of that API call, because LSIs can only be created or deleted at the table creation time. So now what we want to do is to go into our create table operation here and search for indexes, and there is a function here called local secondary indexes that accepts a local secondary index data structure. So we'll have to construct that very similar to what we did with the key schema element and the attribute definition data structure. And you also have the option to create global secondary indexes, right? And that has a separate data structure called the global secondary index type. But for now, we're just going to be focusing on LSIs. So for our LSI, let's go ahead and construct one of these LSI objects somewhere right up here. So we'll say LSI1, because we could have more than one LSI, is going to be a local secondary index builder. We're going to go ahead and use the default function here to create a new builder. And then we can specify all of the options on our LSI. So first of all, we have to specify an index name. And I would encourage you to check out the REST API documentation for create table here. So for the local secondary indexes, this is going to be an array up to 5 LSIs on the table. So you're limited to 5. And then if we drill into the local secondary index type here, you'll see that the index name field is required, yes. And then we also have to specify our hash and range key for the LSI. And then the projection down here is required, but I'm pretty sure the SDK actually handles that for you, even if you don't specify it. I tested this out previously and it didn't require me to specify it. So let's start by the simple things here. Index name. We'll just set this to Trevor, or actually Rust DDB products LSI dash is available index. So now the index has a name. We also need to specify the key schema. So the key schema is going to be the same partition key. Remember that we cannot have a different partition key for the LSI. It must match the underlying table. So we're just going to reuse the partition schema here, but we need to clone it because Rust consumes the value when we reference it. So what we're going to do is say part schema. And if I save that, you'll see we get an error down here. Eventually, let's comment that out really quick. You'll see it says use of moved value, value used here after move. And that's happening because when I reference it the first time, it's actually consuming that value. So here, I'm just going to clone the value, and then it will still be valid to use the second time right down here. And then what we're going to do is go ahead and specify the other key schema, which is going to be our range key. But in this case, we're not going to reuse the range or sort key that we have for the underlying table. We actually want to create a different one. So I'm going to create a duplicate of my range key here. And we're going to specify this as index sort schema. So that'll be a unique variable for that. And then the attribute that I want to be my sort key is available, right? I don't want to use the p name because that's the sort key for the underlying table. I want my index to have a different sort key, which does not have to have unique values because it's part of the index, not the underlying table storage. So I can have yes, 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 no, no, no for is available as my range key. And as long as it's in the index, not the underlying table, it's totally valid. So now for the key schema, I'll say go ahead and add my index sort schema there as well. And now I can take this LSI builder, call the .build function on it, and that will give me this result. And we'll say .unwrap here as well. Just put that on a new line for readability. And now we actually have the local secondary index data structure that we need to pass into this function right down here to configure the table creation with the LSI. Now we're going to get an error here, and I'll show you why this happens. Well, first of all, if we try to create the table on top of itself, that is not going to work. So I'll just come into the console and delete this table manually really quickly. Shouldn't take very long to delete because it's just a very tiny table. It doesn't have any items in there. So let's go ahead and do a cargo run here again. And that'll recompile our application. Now we get an error here saying that our projection is empty here. So it's saying that the projection failed to satisfy constraint. So I guess I did actually add that in. So let's do dot projection, and then we'll use this projection type here, which I believe is an enumeration. So DDB types projection is where it's located in the crate. And we'll just do double colon, and then we'll say builder. Actually, let me see. Do a projection builder. Then we'll do default. Then we'll go ahead and set the projection type to projection type. And I believe that is an enumeration. Let's do projection type, and we'll just say all right here. So I'm going to extract that and actually put it into its own variable. So let index projection equal the result here. We'll go ahead and call .build on that. And for some reason in this particular case, it doesn't give us a result, so we don't have to unwrap it like we did with the others. When we call build, it actually just gives us the projection structure right there. So now we can take that projection structure and pass it into our LSI configuration. So that should satisfy this error saying that the member must not be null for the LSI projection. And the little .1 here, remember that the API for creating a table actually allows us to specify up to 5 LSIs, right? So under local secondary indexes, we can pass in up to 5 LSIs in the request data structure right here. And so it's simply referring to the first of an array of elements here. So anytime that you see that .1 or .2, .3, .4, etc., it's referring to a specific index that you are attempting to pass in to your create table operation. So let's try doing a cargo run again, now that we've fixed the projection right there, and we should receive another error message. And in this particular case, it's going to say some index key attributes are not defined in attribute definitions. And it actually tells you right here what attribute definitions we've declared. So we have p category and p name from the underlying table. Those are the hash and range key for the underlying table. But then the keys that we have here for the index are p category and is available, right? And that's based on the schema right here. So we have our partition schema, which matches the table for our LSI right here. And again, we had to clone that because we didn't want to consume it. And then our index's sort key is available. So it's actually telling us that one of the keys from the index declaration is not found in the attribute definitions. And the reason that we're seeing this particular error message is because when we specify a new sort key for the LSI, we actually have to add that sort key to the attribute definitions in the underlying table. So what we need to do is actually add another attribute definition here. So I'll duplicate this one and say index sort attribute. And we're going to set this one to is available. And then we're just going to add a third attribute definition into our table creation here. So previously we just added our partition and sort key for the table itself, but when we have an LSI with a different sort key, we actually have to add in more attribute definitions so that DynamoDB knows that we're going to be using a specific attribute as a sort key for the LSI. So let's do index sort adder right there. So now we've added our 3 attribute definitions, the category, the product name, and the is available for the LSI. We added the LSI configuration itself right down here. So I think this should work now. Let's do another cargo run, recompile our application, and this time we didn't get any errors. So that means that there was not an error condition right down here on line 45 that would cause the error to get printed out, so it should be successful. If we head back over to the console here, do a refresh, you can see that my table has been created successfully here. And if I head over to indexes right here, you can see that I do have this index down here with the same partition key. Again, that always has to be the same with LSIs. I know I've said that several times. I'm just kind of trying to reiterate that. And then the sort key down here is different. It is available as a string instead of p name as the string sort key for the table itself. So now I can go ahead and start adding items into this table, and then I can query them both on the hash and sort key, hash and range key at the table level, or I can query them by querying the index like what we showed before using the console. So my main key takeaway here for this particular video is that the LSI is a handy utility that you can use to query data differently using a different pattern. And we also learned how to actually define an LSI in Rust code. So if you're building an application that needs to be able to replicate tables across different regions, or if you have lots of different complex table configurations and you want to create them from an actual Rust application to manage across many AWS accounts and many regions, this is how you can actually call the underlying REST APIs using the Rust programming language to create the table and the LSI all in a single operation. In any case, I hope you learned something new from this video. If you're not familiar with Rust, I would strongly encourage you to learn about Rust because it's a very high performance language, and it's actually being backed by a lot of major companies, including Microsoft, Amazon, and Google, along with many other companies out there. It is a very high performance application programming language though, so it is really great. It's very efficient with resource utilization, so it's great for putting into Lambda functions. It's great for scaling in container solutions like AWS Fargate. It's great for running on just EC2 instances as well. You can oftentimes get the same performance using a smaller EC2 instance type than higher level programming languages that are not as efficient with CPU and memory utilization. So in any case, Rust is a great language. The SDK is generally available as of November 2023, which is the reInvent timeframe for AWS. And so I hope you enjoyed this video, learned something new, and learned something about the Rust programming language and the whole Crate ecosystem of packages for various APIs. Thanks for watching, and we'll see you in the next video right here on the Stratus Grid channel. Don't forget to like this video and subscribe to the channel for more content. Thanks.